Hi everybody, welcome to Calculus 3. We'll go over a few problems that we need to know. Most of these problems come from Calculus 1 and Calculus 2. Some basic problems. First we have the derivatives. Right, so we should know derivative of a polynomial, exponential function, and trigonometric function. Alright, now we take derivative. 2x squared derivative will be just 4x negative 5e to the 3x, e to the 3x, derivative of e to the 3x, of just x, would be the same thing. So we'll do 5e to the 3x, it's going to be the same thing, except this time we have to take derivative of the exponent. Right. Next, derivative of 7 tangent of 2x. Derivative of tangent x in general is secant square. So we're going to have 7 secant square of 2x. And then derivative of inside of 2x is going to be 2. Right. So we have 4x. 3, that's 15e to the 3x. 7, 2, that's 14. Secant square of 2x. Right. Next we have the derivative of square root of sin x plus 5. Square root I will write as sin x plus 5 to the 1/2. And then we take derivative of something raised to the power 1/2. I'm going to write 1/2, take down the 1/2, and then the parentheses, doesn't matter what it is inside. The power, apply the power rule, we have 1/2 minus 1, so that is minus 1/2. And then derivative inside the parentheses, we have cosine of x. And so the parentheses is just sin x plus 5. And we can multiply the cosine x and the 1/2. The sin x plus 5 to negative 1/2. We cannot do anything with it. We cannot mess with it. So just say cosine of x over 2. And then we just write like that. If we want to, the negative exponent, we write that at the denominator. So I move this down. Negative 1/2 moves down to the positive 1/2. And 1/2 power equivalent to the square root. So we can say cosine of x over 2 square root of sin x plus 5. Right. So that's what we have. Right. Next we have implicit differentiation. And in this particular, we won't find dy over dx. Dy over dx, when we see dy over dx, we mean that y is a function of x. If y is a function of x, when we take derivative, that's going to be slightly different. Right. Now, if we take derivative of this with respect to x, so we just say differentiate with respect to x. Right. Notice that we have x certainly has x in it. Y is a function of x, so y has x in it as well. So what we have there is the product rule. So if we write u and v, kind of small, so I brought it here. U is going to be x, and v is going to be y. Then we take derivative of u, which is derivative of x, which is just 1. So that's easy. Derivative of y or derivative of v is going to be 1. However, by the chain rule, y is a function of x, so we're going to have the y prime attached to it. So v prime is going to be just y prime. Right. And then the product rule is going to be u prime v plus uv prime. Right. So now the first one is the product rule. We take derivative of that. So u prime, I'm going to just say it. It's going to be u prime v plus u v prime. Right. U prime, that is 1 times v, that is y. U is x. V prime is y prime. I'm using red here. By the way, we can either write y prime, we can also write dy over the x if we choose to. Alright, so that's just the first term. Next, derivative of x is 1, and derivative of 2, it is a constant, so it's going to be 0. Alright, so that's pretty much, we have y plus x times y prime plus 1 equal to 0. So we move the 1, we move the y to the other side. Xy prime equal to minus y minus 1. And finally, if we solve for y prime, or we can write dy over dx equal to negative y negative 1 over x. Right, so that's what we have. Right, so here y is a function of x because we're looking for dy over dx. The next part is called the related rates. We have assumed that x and y are a function of t. So we have everywhere x is a function of t, y is a function of t. We are given dx over dt, x and y. Right. Obviously, we can just take derivative directly here with respect to t. However, just like implicit differentiation, we can manipulate the equation so to have something easier to take derivative. What I do is I'm going to square both sides. If we do that, we should have y squared x plus 1 equal 144. Right. We can multiply it out. However, I'm just going to keep that directly because that is a product rule. So similar to what we have on the previous problem. Let's say this is u and this is v. Now we differentiate with respect to t this time because we need to have dy over dt. So differentiate with respect to t. Right. So it is the product rule. So I'm going to write here u is equal to y squared and v is equal to x plus 1. Now this time we take derivative with respect to t. And both x and y are a function of t. Right. So derivative of y squared, derivative of anything squared is going to be 2 times that, so 2y. But since y is a function of t, we're going to have to put dy over dt next to it. That is derivative. Now v prime, derivative of x is just 1. However, we have to have dx over dt because x is also a function of t. So that's what we have. And then we substitute into the product rule on the left hand side. U prime v plus u v prime. U prime is 2y dy over dt. By the way, this review I write a little more detail. You can skip a few steps. If everything is clear, you just skip a few steps. Right, so u prime v and then u, that will be y squared, and v prime, that is just dx over dt. Derivative of the right hand side a constant, derivative of a constant is 0. Right. Now we're going to evaluate at these values. I'll substitute those values into this equation. Right, 2y, y is 3, and then dy over dt. I'm just going to write using red because that's what we're solving for. X plus 1, x is 15 plus 1, y squared, that's 3 squared, dx over dt is 8 equal to 0. So we have 2 times 3, that's 6, 15 and 1, so 6 times 16, that's 96 dy over dt. And 3 squared, that will be 72. And so for dy over dt, we have 72 negative 72 over 96, which is negative 3 over 4. Right. So this kind of similar concept. Here we have x and y function of t. So when we take derivative, it has to be the chain rule. Same thing on the previous one. But this time both x and y function of t, because we see that in the question. So that means we take derivative of everything with respect to t. And the last point I try to make is if somehow we can turn the equation to something easier to take derivative, we do that because the equation is still balanced. Derivative with the square root from the beginning, it could be a little more complicated. Right. Given slope, I'm going to write y minus y naught equal to m x minus x naught. So that is the equation of a line go through the point x naught, y naught, and the slope is m. Right. In this particular, if we know the function, so we can rewrite that as y. Instead of y naught, we say the function at that point equal to the slope. The slope is given by the derivative at that point, x minus x naught. So in our problem here we are given the x naught is 4 and the function is x cubed minus 16x minus 3. Right. So we have the function is x cubed minus 16x minus 3 if we evaluate at x equal to x naught equal to 4, we're going to put 4 in for x, 4 cubed minus 16 times 4 minus 3. Well, that's convenient. 40, 64, 64, so that's just negative 3. And that negative 3 is going to go into the values of the function. Right, then we'll take derivative. 3x squared minus 16. We're going to put 4 in for x. Derivative is 4. 4 squared minus 16. 4 squared 16 times 3, 48 minus 16, that's 32. And the 32 will go into this. So we have here that part is negative 3. And the derivative 32. And x naught here, of course, is 4. Alright. Just put the formula in the box. So that equation of tangent line of a function at a point. Right. So y minus negative 3 is that y plus 3, 32, x minus 4. Multiply it out, move the 3 over, y equal to 32x. 32x minus 4, 128 minus 3, 131. Right. So that is the equation with tangent line to the function at the point. Right. Next we have linear approximation. This almost the same as what we just did. We just need to roll. We're going to estimate the values for y. So for that, this equation we turn into. We just need to move the f of x naught to the other side. It becomes y equal to f of x naught plus derivative at x naught, x minus x naught. Right. Now we just need to determine what is x and what is x naught. So the values we try to evaluate is 16.39. That's going to be x. Because we want to evaluate at that values. The x naught though, we have to choose something that is nice, even, and easy to evaluate. So square root of something nice and even that is close to this. Because the 16 come to mind. So we let x naught be something close to it, but the number is very easy to evaluate. So we're going to use 16 because square root of 16 is equal to 4. So that's the point of approximation. We're trying to find the point, the x value that's close enough, and we can manage at least by hand. Right. So if x equal to this, replace x into that number, we have square root of x, and that is the function. So whatever the numbers on the problem, that's going to be x, and we have the function of x. Now we evaluate that at x naught of equal to 16, so f of 16 square root of 16 equal to 4. So that's what we want to put here. That is going to be 4. Next we have the derivative. This is x to the 1/2. Derivative is 1/2 x to the negative 1/2. And similarly, we're going to put 16 to it. That 1/2, 16 to negative 1/2, I move it down. It becomes 16 to the positive 1/2. Well, that like the square root, so this is 1 over 8. So I'm going to put 1 over 8 here. And we have x, and we have x naught. And put everything together, we have y equal to. In fact, it is approximation, so we can also write that as approximate instead of equal to. The values of the function for the slope or the derivative 1/8. The actual values for x 16.39. The approximation something close to it 16. Right. I need a calculator here. Uh, 4 plus 1/8 times that is 0.39. So that's what we have. 4.04875. Oh, the 4 decimal places. So let's say is it 4.048 and 8. Right, so that is the first application of derivative as a linear approximation and equation of tangent line. So pretty much what we approximate is actually I can draw a little graph here real quick. We have the function square root of x look like this. Let's say this is x equal to 16. We want to find what 16.39 this point. We try to find this y values. Kind of difficult to find it on the curve, so we're going to draw the tangent line at 16, and we say the values of the line is extremely close to the values of the curve, hence linear approximation. So we use the tangent line to approximate the values of the curve. It only works if the function, if the point is extremely close to x0. So that's why 16.39 is good. If we estimate like 20.5, it is way out here. It's not good because it's not close to 16. So it have to be very close to the point that we have the nice values. Otherwise, it will not work as well. Right. Since we have the calculator, if we want to square root of 16.39, as you see, those numbers are pretty close. Right. Next, we have another application of derivative. Is increasing, decreasing, and therefore give us maximum and minimum. So we have this function. First we find critical values. Critical values is where the derivative equal to 0 or derivative does not exist. This is for the critical values. Not only that, whatever values for x, the function has to be defined. So notice that the first thing here, x cannot equal to 0. So whatever it is, x equal to 0 cannot be a critical values. Right, keep that in the back pocket. Right, so bottom line is we need the derivative. Right, so take derivative of this. I just copy the function. However, instead of write 4 over x, I'm going to write 4x to negative 1, and only then I will take derivative. It will be easier in this form. Take down the negative 1, negative 4x to the negative 2. So 1 minus 4, negative 2, x to negative 2, move it down, becomes x squared. Common denominator of x squared, we have x squared minus 4. Right, so that is the first derivative. Yeah, much better. I just need to change the line here. Alright. Now, back to the critical values. We need to have derivative equal to 0. If we have fraction that is equivalent to the top equal to 0, and does not exist that equivalent the bottom. If it is the fraction, that is where the bottom equal to 0. Just run out of ink on the so just going to do that. The top equal to 0, x squared minus 4 equal to 0. So in that case, x equal to, we have x squared equal to 4, meaning x equal to, don't forget there's plus or minus square root of 4, which is plus or minus 2. Bottom equal to 0, we have x squared equal to 0, which gives us x equal to 0. So the critical values we have x equal to 0, x equal to 2, or minus 2. I just put plus or minus 2. Only one thing though, we did mention that whatever the critical values is, the function has to be defined. So in that case, we don't have this x equal to 0. So critical values, we don't have x equal to 0. Right. So that's what we do when we take derivative. Take derivative and then equal to 0 does not exist. That gives us the critical values. But notice that the function has to be undefined. I mean, the function has to be defined at those values of x. Right. Need to replace the ink here. Right. See if it works. Right, it works. Right. So we have critical values of 0, plus or minus 2. Right. So we have critical values at only 2 and negative 2. Next we'll use the first derivative test to locate the maximum and minimum. Notice that what we have now is the derivative and the critical values of 2 and negative 2. Actually we're going to use 0 also. Right. So what we do here is we're going to put on the sign chart. So I'm going to draw a sign chart. It will be as follows. Just a light table. Right. The top we have the values for x. So it is line a number line. We have like negative infinity to infinity here. Critical values, we're going to have negative 2, 0, and 2. At the middle though, we have the derivative. So we just write the second derivative. First derivative is x squared over 4 minus 4 over x squared. Right. We do know that when x equal to negative 2, derivative equal to 0, and it does not exist if we put 0 in here. So we write d and e here, and at the bottom is going to be the function. Right. I will divide this, so it will be like a table. Right. Next we're going to choose the point in between each interval. So I choose negative 3 here, negative 1, 1, and 3. I'm going to put those values into the derivative. So negative 3 x squared to negative 3 put in for x. It's going to be 9, and of course we can do this on the calculator as well. Let's say I'm going to put the function into y equal to This one we can easily do by hand, but I just want to show that on the calculator quickly. Alright, then we just go to the table. Alright, because it's undefined at 0, at -3 it's going to be positive. -1 it is going to be -1, -3, positive. So positive is increasing, negative is decreasing, and increasing. Based on that, we're going to have the max here and the minimum here. We only locate, so here we write the maximum, the local maximum, at x equal to -2, and local mean at x equal to 2. Right? So the derivative tells us increasing or decreasing, and based on that we can find the maximum or minimum. Right. The second derivative test, we're not going to use this chart. We just use derivative to test the point directly. So remember, the first derivative we can use any of this. I'm going to keep this one because that is easier to differentiate. So I'm going to this is the first derivative, and we take the second derivative. It's going to be derivative of 1 is 0, derivative of this is 8 times x to -3, or 8 over x3. Right, just derivative of that. Right. Now we will evaluate as 2 and -2 at the critical values. So at x equal to -2, we have second derivative as -2, 8, -2 cubed. That is 1, -1, less than 0. If it's less than 0, it will open down, and we have the local max. And then at x equal to 2, we're going to put 2 in for x, and we have 1, which is positive. Positive is concave up or open up, therefore it has the minimum. So if it's positive, the function concave up, and we have the minimum. If it is negative, the function concave down, and we have the maximum. Right. So that is the first derivative test and second derivative test. Right. Next we go to integration. First integrate. Right. This we have both sine and cosine. The rule of thumb when we evaluate the integral of both sine and cosine, we base on the power. If it is odd on cosine, we're going to let u equal to sine. If it is odd on sine, we're going to let u equal to cosine. And if both of them is even, then we have to use the power reducing. Right. Since here the power is in the odd, so we know that the substitution has to be the order function. It's always the order function. So we're going to say let u equal to, again, odd go with cosine, so u is going to be sine of 5x. Need to change the contrast a little bit, a little bright. better. If u is equal to sine x, then we can take derivative. Will be 5 cosine of 5x dx. And now I'm going to divide by 5 on both sides. So we write du over 5 equal to cosine of 5x dx. Right. So why do we have to write like that? First of all, we're going to have the sine, which is going to be the u. So we have sine square, so that is u square. So that is u square. Next, we're going to need to have the cosine of 5x dx. So this one I'm going to split in two. First it's going to be cosine square, and then cosine. So we split the cube into a square and the first power, and we still have dx there. And then next we have cosine 5x dx. That is exactly du over 5. So this thing here is du over 5. Right. We still have u square there. Cosine square, we have the Pythagorean identity. Cosine square plus sine square is 1. So for cosine of theta, and we substitute that in here, we're going to have 1 minus sine square 5x, right? And again that will turn into a u square. So pretty much we have u square 1 minus u square, and the 5 here is a constant, which is outside but have to be at the bottom. The rest is simple, it's just a polynomial now. So it'll be 1/5 u square minus u to the 4th power du. Integral is 1/5 u square integral u cube over 3 u to the 5th over 5 plus c, and u is sine of 5x. Sorry. And we can just leave it like that. So the integral, where we have sine and cosine, the power of sine, cosine, whatever the odd power is at, we let u equal to the order function. Since the odd on the cosine, u equal to sine, and it should work out all right. Right. Next we have this problem. This is integration by parts. For integration by parts, we used, let's just write the formula. Integration by part, integral of u dv equal to uv minus integral of v du. Right. And what we let u be, usually u is something to be differentiated. And usually we'll use this rule of thumb. So that logarithmic function, inverse trig function, so log, inverse trig, algebraic, this including any polynomials, trigonometric function, an exponential function. You should have this on the handout. But on here what we have is we don't have the log, we don't have inverse trig, but we have a polynomial here. So that's what we're going to let equal to u. And usually iteration by parts, I'm going to use the table. So I'm going to put the table like this. First we choose something to be differentiated, and that is the u, so be x squared minus 3. So this to be differentiated, so we just take derivative. 2x derivative is 2 and 0. Everything after that will be 0. And then the other one will be integrated. E to the 2x, we integrate 1/2 e to the 2x. And then another 1/2 coming out, that 1/4. And another 1/2 coming out, that 1/8. Right. And then it is the diagonal positive, negative, and positive. Right. So the integral of e to the 2x, x squared minus 3 dx. So first one we have first diagonal, we have x squared minus 3 1/2 e to the 2x, and then minus the next one is 2x 1/4 e to the 2x, and then the last one is positive 2 1/8 e to the 2x plus c, which equal to just simplify just a little here, put 1/2 in front, e to the 2x, x squared minus 3, 2x minus 1/4, that is minus 1/2 x e to the 2x, and then just 1/4 e to the 2x. We can also factor out the e to the 2x, but I'm just going to keep like that. Again, that is integration by parts, and the order to choose u, and when possible I use the table. Next, we have the trig substitution here. You should have this on the handout. If we have x squared plus something square, that's going to be tangent substitution. X squared minus a constant square, that is secant. Constant square minus x squared, that is sine. So in this case we have, let x be tangent of theta. I'm sorry, not just tangent of theta, have to depends on that. 49 is 7 square, so we're going to have to put 7 there as well. Alright, then we can take derivative. Dx is equal to derivative of tangent is secant square right. I'll substitute everything into this integral. First I'm going to write 1 over x squared plus 49 3/2. I'm going to put the dx at the end. Alright, so we have 1 over x squared, so we have 7 tangent of theta square plus 49, all that to the 3/2, and the dx is going to be 7 secant square d theta. Right. still have 1. Multiply it out to have 49 tangent square, and we have 49, so I will factor out the 49, and that's what we have to the 3/2. Still with 7 times 7x secant square d theta. Right. Now 49 to the 3/2. 49 to the 3/2. Quickly. 49 to the 3/2. That's 344. That's 7 cube actually. So first the number. I'm just keep 49 there for a moment. Tangent square plus 1, that is the secant square. We should write 7 square actually. Doesn't matter. So that will become 49 to the 3/2, we have 343. Secant square to the 3/2, 2 and 2 cancel, we have secant cube. Now the numbers, 7 on the top, 343 at the bottom. Seven on the top, 343 at the bottom, and then secant square over secant cube cancel out. We just have 1 over secant. Reciprocal of secant is cosine. 7 over 343, that's 49, and then we have cosine of theta. Integral of cosine is sine. Right. All we need to determine is what is sine. Right. We don't know that, but we do know x equal to 7 tangent of theta. So tangent of theta equal x over 7. We can draw a triangle. X is the opposite, adjacent, and the hypotenuse. Pythagorean theorem, we have x squared plus 7 squared, or x squared plus 49. And in that case, sine is equal to opposite over hypotenuse. And we substitute back in here. We have x over 49 square root of x squared plus 49. We just substitute that in here. Plus c. Right, so that's what we have. Right. Right. So that is the trig substitution. Again, in this case, x squared plus a constant square, so that is the tangent. Right. Next, we have a few application problem. So first, we're trying to set up the integral to calculate the area under the curve. So first, we have the curve y equal to square root of x. That's going to be this curve. Y equal to x plus 2, y equal to 8. When x equal to 0, y equal to 4. When y equal to 0, x equal to 8. So we have this point and that point. Where's the ruler? and then finally y equal to 0. Of course, that is the region we're talking about. This one we do both dx and then dy. Now dx, if it is dx, we're going to multiply by the height like this. There's a problem with that. There's no inconsistency between from here the function above is the red curve, the bottom is y equal to 0. On this side the function above is the blue line, the function below is y equal to 0. So in that case, if we set up the integral for using dx, we have to split. For this part, will be integrate from 0 to 4. The top function square root of x minus bottom function 0, so we just have that. And then this one from 4 to 8. The function on the top is something in terms of x, so we're going to put that here for now. Right. X plus 2y equal to 8. If we solve for y, 2y is equal to a minus x. So y is equal to a minus x over 2. Right. Next, if we're going to use dy, we still have the curve. And the line. Y equal to 0. But this time we're using dy. So in that case we have to use from left to right here. By the way, if it is dy, the limit for y of just from 0 to 2. Right, so from 0 to 2, if we looked along the x-axis, we're going to see the red curve on the left, the blue line on the right. So we have the right function minus the left. The function on the right is this, but notice that it has to be in terms of y. So from here we can say x equal to a minus 2y, and that is the function on the right minus the function on the left, but in terms of y though. So y equal to square root of x, y squared is equal to x, and we have to use the function in terms of y. We can evaluate both of them, and that will be the same. Right. Next, chain between the rectangular and polar. This is what we need to know. R cosine is x, and R sine is y. We have x squared plus y squared equal to r squared, and tangent of theta equal to y over x. So we have that. Right. Of course, we can just draw a sketch. This is x values, y values, theta, and r. X squared plus y squared is r squared. Tangent is opposite over adjacent, and then all the other tricks that should check out. Right. So we have r sine is equal to y, r cosine is equal to x, and r squared equal x squared plus y squared. So what I do here is multiply by r on both sides. So we have r squared equal to 32 r sine of theta, r sine of theta, that is y. So we have r squared equal to 32y, r squared is x squared plus y squared equal to 32y. And we have the equation in terms of x and y, so which is good, that's what we want. Next we have this question. So we have the equation given by r equal to 9 plus a sine theta, theta equal to 0, and the question asks us for the slope. Right, the slope is dy over dx. Now the problem is both x and y are function of theta, so we can say dy over d theta over dx over d theta. Of course, that's what the formula we're going to use. We can also rewrite this, multiply reciprocal, if you will. So flip it, and we cancel dy by dx. Right, so pretty much we're going to find dy over d theta and dx over d theta. So we start with something fundamental. X is equal to r cosine theta. R is this. Cosine theta. Multiply it out. 9 cosine theta. A sine theta. Cosine theta. We will take derivative with respect to theta. Derivative of 9 is negative cosine. Derivative of cosine is negative sine. This I'm going to use the product rule. Derivative of the first, a cosine theta, times the second, plus the first with derivative of the second. Derivative of cosine is negative sine. Negative sine. Right. Just rewrite this a little. Negative 9 sine of theta. A cosine square minus a sine square. Now we have theta equal to 0, so we will evaluate at theta equal to 0. Derivative equal to negative 9 sine of 0. A cosine square of 0, that is 0, not theta. A sine of 0, right. Sine of 0 is 0, cosine of 0 is 1, so that will just give us 8. We'll do the same thing for y. Y equal to r sine theta. It is 9 plus a sine theta times sine theta. Multiply them out. 9 sine theta, 8 sine square. Derivative of sine is cosine. This is the chain rule, so take out the 2, and then derivative of sine is cosine, and then we evaluate at 0. Cosine of 0, 16 sine of 0 cosine of 0 sine of 0 is 0, so that one gone. Cosine of 0 is 1, so this is equal to 9. And finally, dy over dx is dy over d theta dx over d theta, so which will be equal to dy over d theta is 9 and dx over d theta is 8, so that's 9 over 8. The last problem we just have the formula to calculate the area between the two polar curves. It's not really important how to the formulas here. The objective of the problem is just how do we set up the integral. Right, the integral. I'm going to write the formula first. It is between something, let's say alpha and beta, 1/2 the big radius square, should be, let's just say the function of theta square minus a little function square. Now let's look at the problem. It is outside of the circle and inside the cardioid, so it will be actually outside the circle, so and inside the cardioid, so we're talking about this one. Now, in this integral, what we see is it's from this point to that point. We can verify that this is equivalent to 0 to pi. Actually, we can let these two functions equal each other. Let's do that quickly. R equal to 3 and R equal to that, so 3, 1 plus 3 sine theta. Multiply them out. So that gives us sine of theta equal to 0, which of course 0 and pi makes sense here. So let's just graph that to make sure that this is what we have. So turn on the calculator here. I'm going to plot in the polar mode. And make sure in gradient mode also. Y equal to 3 and then 3 1 plus sine of theta, that is theta, and we see the graph. Right, just to make sure that, let's zoom number 5 so they have the right scale. Right, now we only need that upper half, so let's hit Windows. This time we go from 0 to pi, and how many points do we graph? Let's say point pi divided by 100, meaning that we're going to plot 100 points from 0 to pi. And let's see it. Right, so that's exactly what we have. So that is from 0 to pi. Next, the outside function. The big function minus the little function. From the graph, we have the perspective is from the center, so we look from the center, looking outside. Every direction. When we do that, the first function that we see is going to be the part of the circle here. So we see the circle inside first, so that is the little r, the little function. After we see that function on the outside, constantly we see the part of the cardioid. So the cardioid is going to be the big radius. The big radius, the cardioid, 3, 1 plus sine theta. The big way is square, the big function square minus the little function. The little function is just 3 square. Yeah. So objective is not to find the area, you just have to set it up in calculus 3 later on. It is very essential, very important that we need to know when we set up the integral. In this case, the inner function is the circle, the outside is the cardioid, and the outside square minus the inside function square, and that's what we have. Right. So actually that go over everything. That just only a few things we need to know before we take in calculus 3. I hope you find this helpful. Thank you for watching.